Afternoon. So I just wanted to go through the solutions to the worksheet that you had yesterday. I asked you to look at question 1 of the forces due to magnetic fields questions. Now these were questions that came from the practical paper, and they're ones that I'd selected that sort of tied in with one of the required practicals. Unfortunately, they never in the exam just give you the exact practical that you've learnt or done. It's loosely based on it. No, actually, in my blurb yesterday in the email, I said it would require lots of the skills you'd done. And going through the answers, there actually wasn't anything in this question about percentage uncertainties or any of that. So there will need to be a couple of questions on that coming up. But it was still very much practical based. It was knowing what you needed to measure, what you needed to plot. And of course, in those questions as well, they would penalise you for not using the right number of significant figures and so on. So you need to pay attention to that. So I've got the question over sort of there. So I'm going to keep looking over there to go through this. If you get it up on your screen, it was question 1. I'll show you briefly what it looked like. It was that one there with the ruler pivoted over the scale. And the first thing that we were asked, and I won't read all the writing, you've got it in front of you, so you've got the idea. It's sort of attached to the clamp stand, and then it rests on that prism. And it was closer to this end. This was 30 centimetres. They told us that this was 1 centimetre here, where it was actually clamped, and the whole thing was a 1 metre rule, and we were given a reading on here as well once the ruler was allowed to rest. So the first question was to get the mass of the ruler. Now actually this was just a moments question. It seems, looking at it, that it would be easiest to look at this as a pivot and try and work out moments like that, but actually I think the easier solution is to take this as the pivot here. And because this ruler is 1 metre long and this was only 30 centimetres, that meant the weight of the ruler was actually on this side of the glass prism. So what we've got here is a certain force, and they gave us that number. That was, let's just write that on, 214.66 grams on the scale there. So we know that that is the force acting at that point. And what we're going to try and do is, using this as the pivot, we're going to say, okay, well, the weight of the ruler is acting down here. As you look at it, that is a clockwise turning force at a distance of, well, I'll come to that in a moment, but whatever we work out this distance to be. And we're going to put that equal to, and this is where you may have been a little confused, the force here upwards. So okay, the ruler is pushing down here. Okay, but when we look at this in terms of moments, what's stopping this ruler collapsing like that? Well, it's this prism pushing up. So actually, that's the force going up and giving us the anti-clockwise turning force. So if anti-clockwise is equal to clockwise, I just write this out here. My clockwise one was our weight of the ruler, which we didn't know, multiplied by, and this is why I didn't mention the distances earlier, because we've got 2 options here. This is going to be in the centre of the ruler, so we can call it 50 because it's a metre ruler. If we were doing that, we'd have to call this one 30 because that was 30 centimetres from the end. Now actually the values we should be using, which will give us the same answers actually because they're both out by a centimetre, should be a value of 29 and 49 because we've got 1 centimetre overhanging here. So let's just use those. So the weight of the ruler was at 49, and the anti-clockwise turning force was what our prism was pushing back up with, which was 214.66. I'm leaving this in grams because they're fine with the answer, the weight of the ruler being in grams. In fact, it tells you, I was just checking, it tells you need it in grams. So I'm going to leave that as grams, and the distance of that pivot was 29 centimetres. So I've got my anti-clockwise and my clockwise, and I know that those two are equal to each other because this thing's not moving. So I would work this one out, I would divide by 49, and I'll get the weight of the ruler, and the answer was 127.04 grams. Now that actually should have been rounded to 127, because for our ruler we were given a less accurate reading. We were told, I'm just looking for the data here, one decimal place actually, so that shouldn't be 127, it should be 127.0, just so we're doing that to the same number of decimal places as the ruler measurements. On that particular question, they were okay with just 127. They were also okay with 127.0. So they weren't actually being too fussy there for a practical question. It's a method that was the important thing there. And then you're asked to state one assumption that you make. Well, it's usually the same with these ruler, moments, balancing stuff questions. We're assuming this ruler has a uniform mass. In other words, that the mass is distributed uniformly along here, which is the only reason we can put that weight of the ruler as being in the middle. If it wasn't, if it was slightly heavier at this end, then obviously that arrow shifts slightly that way, but you don't get those generally. Now you're off to uni soon, so you need to start using some proper words. We would say that the mass of the ruler was homogeneous, which means that it's the same throughout. That would be a better way of putting it. Down to the next part of the question. If my computer will allow me to scroll. Oh, seems to have frozen that. This time, let me just remind you, in case you're not looking at this, we've now taped a bit of wire along the top of the ruler, and we've put a magnetic field either going into or out of the page. We don't know, that's what we're trying to work out. Here's the sort of bigger picture here. If you're looking at this on a small screen, this is going to be impossible. If it's on a larger screen, you'll see it, or you'll have it in front of you. So it's just this little region here. So depending on what effect this magnetic field has, it's either going to be pushing the wire down or up. How do I know it's going to be down or up? Because, well, first, it's obvious in the way they've laid out the question, but secondly, if the field is in or out, then we know that the force that's going to be produced is going to be perpendicular to that. That's why we have Fleming's left-hand rule. We've got a new reading here, and that has gone slightly up as well because we've placed a wire on the ruler, which has added a little bit of weight, but we're told that these terminal blocks here don't add any weight. So for this one, this does like to freeze up for some reason. Okay, here we go. So for this one, what are we asked? Well, actually, we are given a graph of how the balance reading changes with current. And we can see that as the current goes up, which is along the x-axis here, as that goes up, the mass on the balance is actually going down. So as we're putting a stronger current through this wire, that reading's going down. So let's think about that. If we're putting a stronger current through the wire, that would mean that whatever force that current was having in conjunction with the magnetic field would be getting stronger as well, no matter what we do. Now, if the balance reading is getting less, then in actual fact, it must be pushing the wire up. Okay, that's the only explanation. Remember, it's fixed at this end here. So if this pushes the ruler down with more force, that's going to increase. Pushes it up, it's going to decrease, and that's what we're seeing is a decrease. So, I apologise for small delays here. My computer seems to go to sleep very quickly, and I have to wake the document up. What are we asked about this graph? Well, first of all, we're asked to state and explain the direction of the uniform magnetic field, and there's 3 marks, so it's not just enough to say it's into the page or it's out of the page, whatever you work out. You need to say how you work that out, explain. So you'd say I'm using Fleming's left-hand rule. You've got the battery symbols on the diagram, so you can see which way is positive, which terminal is positive, sorry, and so the current, conventional current, the way the arrows point on the diagram, is positive to negative. So still people at A2 ask me which one is which. Okay, the big one is positive, so our current, according to Fleming's left-hand rule at least, goes this way. Okay, we know that the electrons actually go that way, but still current goes from there. And when you work that out using Fleming's left-hand rule with your second finger following that path from the big terminal of the battery round to the small one, and knowing that the wire is being pushed upwards, you actually find out that it's into the page. Ooh, into the page. Oh, my nails are dirty, I've been gardening, sorry. So we're going to state and explain that, get those 3 marks by saying I use Fleming's left-hand rule. I know that the ruler is being pushed upwards, so the finger that was identifying force was up, and that meant that the field was into the plane of the page. Then we are introduced to a little equation that we haven't seen before, and that is one of the features of these practical type questions. We do get equations that you've not done, maybe equations that don't exist other than for this specific experiment. Okay, equations aren't just these kind of generic ones that are on formula sheets. You come up with equations to suit what you're doing. You'll learn, you do a lot of this at university, that suit your particular model or your particular experiment. And the equation they give us, rather than showing you the tiny screen again, I'll just quickly draw it. We're told that it is this, okay, and that the sigma symbol at the top is the change in force per unit of current. L is the length where the magnetic field cuts through the wire, so it's just that little region, and obviously 3 speaks for itself. We're asked to determine B, the magnitude of the magnetic flux density. Okay, now how could we do this? Well, if B is how much the force changes per unit current, then we can work this bit out by getting the gradient of the graph. Because if you go back to the graph they gave you, that was actually the reading of force. I can't remember whether they called it weight or force now. Let me just scroll back up to the graph. Ah, this is fun. So back up to the graph, what did they have plotted there? They had mass. Okay, so they had the mass reading of the balance, and they had that over the length. Now, really, if we're going for force, which is what we're told this thing is, the force per unit current, then we'd work out our change. So we're going to do this, right? We're going to work out the gradient. We'd work out this change, but multiply it by 9.81. Sorry, I'm off the screen there. I'll explain that again. So this is our change in mass, but we're going to multiply that change by 9.81. So it's a force. This one here, because that is, I have no idea why I've just drawn an L there. That is current, so that one we can just read directly off. So change in force is that multiplied by 9.81. Change in current would be that part of our triangle. One over the other, that's going to give me this value here for sigma. So I went a bit off track there, but hopefully that makes sense. Gradient of the graph gives you that, divide it by 3L, and you get B. And the answer for that one was a range was allowed here, because you're reading off a graph, so they usually do allow a range of answers. Anywhere between 1.76 times 10 to the minus 2 and 1.8 times 10 to the minus 2. Okay, 1.87 times 10 to the minus 2. So actually, just quickly in my head averaging those out, you're looking for an answer that is around 1.8 times 10 to the minus 2. Okay, so that's what you should be looking at there. So that's gradient divided by 3L. Let's scroll down to the next bit. The experiment's now repeated, but with the ruler pivoted at the 90 centimetre mark. I've now just closed those down. That was not helpful. So what we've done now actually is effectively flip the roll around. Let me just show you this on the screen over here. I'm sure you've seen it yourself. So whereas we did have this being closer to the prism than the end of the ruler, we've now got the opposite, where the bigger part of the ruler is here and there's less overhang in here. That tells us that nothing else has changed apart from this, and we have to tick some boxes in some rows of a table. The first one is, how is the force acting on the wire due to the magnetic field affected by changing that experiment like that? Well, if we've not changed the battery, we've not changed the wire, we've not changed the magnetic field, that force won't be affected. That force will remain the same, so you should have had no effect there. Secondly, we're asked about the force acting on the prism due to the pivoted ruler. Now, okay, the force is not going to have been changed, but that force is now further away from that pivot. It's closer to that pivot because we've flipped it round. And so that will mean it will have less of an effect. Think about moments. The closer you are, the less of the effect. The gradient of the graph will also reduce. If the force is less, that gradient was showing us that force per unit current. And if the gradient of the graph and the force acting on the prism are both reduced, then the maximum force, of course, is going to come down. So if that was our original line, okay, it's also going to start at a lower point, so the y-intercept will be less, and we said the gradient will be less, so probably look at something like that. So in summary, for that part of the question, we're looking at no effect, reduced, reduced, reduced. And what do we have next? We now have a lot of writing to read, which I know you don't like. It shows the balance being used to measure the force between two wires, and the connections joining them are not shown. And you are asked to join these, to draw these on, knowing that the currents must have the same direction and be the same size. So I'll quickly sketch this here, 'cause it's going to be easier for you to see than on the screen. There's our sort of two wires, okay, what they called that one wire Y and that one wire X. Obviously the current here is going that way, so I want this one to be going that way as well. And so when I come to draw how that looks connecting to the battery they've given us at the top, what you should have, let's quickly sketch it on here, is something like this. Let me just draw those batteries on as well, actually. So we should have something like this. And what that means is it's one continuous loop. Okay, so it's one continuous loop round, but the current goes that way through that one, and of course it goes that way through that one as well. Okay, so that's all we needed for that. So that's possibly the easiest part of the question. The next thing we are asked we're given another equation that we've not seen before, and this equation is, quickly draw that out, K I squared L over D. We're told that, okay, that the force on wire X due to the magnetic field of Y is given in this way. K is a constant, I is the current, L is the actual length of wire, so those two wires that are sitting side by side parallel to each other, it's that length, and D is the distance between the two wires. So if we're sort of looking at those two bits of wire again that we had before, okay, the two bits of wire, D is that little distance there between them, I can't draw a mirror image, and L is that whole length there. Okay, you've got to essentially say how you're going to conduct an experiment to measure K, but L can't change. You can only, now actually the way it phrases this, you can only have one independent variable. What does that mean? It means you can only change one thing. You're obviously going to be measuring something else. So what you're going to be doing here is changing either the current or the distance. Okay, I would personally have kept the wires clamped in the same place and change the current. Now the problem is, change the current, it gives a bigger force, the distance changes. So one of the things they're allowing in the answers to this is to, well, for that basically, for you to recognise that, that one of them is going to change, but essentially the two of them together form your independent variable. So let's just read through the things we're getting marks for here. You're going to take readings of M, okay, 1 mark, that's the mass on the scale, for different values of, and then you put either current or distance. And you should really say that current or distance, depending on which one you chose, is the control variable. There's a mark for that. It must be clear how the value of the control variable is known. So you're either reading the current from an ammeter or you're measuring the distance with a ruler. L will be measured once beforehand, okay, and you will have a known value for it. You could write that value in here if you want, or you could just say it will be measured and it will have a known value. You should say that because we're trying to work out force here, or should I say we're using force here rather than mass, that we need to multiply our mass values by 9.81. We're already up to about 4 marks here out of a possible 3, so we didn't really have to write a great deal here. We've not even got to what we're going to do to find the answer. Now we are going to need one of our marks to come from that really. They're unlikely to give you 3 marks just for describing the experiment because it's specifically said you're going to use a graphical method. So how are we going to do that? Well, I would suggest the easiest way, we're trying to find out K, remember. If I were to plot F times D, so take D over to the other side here, or multiply both sides by D. If I was to do FD divided by current squared times L, then I would get K directly from my gradient. So that would be what I would suggest in my method for doing this. I would be measuring W, multiply it by 9.81 to get F. Distance will be multiplied by that. Current I'll be reading off the ammeter, square that, multiply by length. And just in case I'm talking too fast, let's just write out what I'm talking about here. FD over I squared L will give me K, so I'm going to make that the gradient of my graph. And that is the end of that question. Not the most exciting thing, but thanks for sticking with it. Practical skills and thinking about how to analyse things is going to come in useful for you guys anyway, even though you've not got exams coming up. Hopefully by now you've watched the solutions video to today's lesson that online teacher was giving. Any problems with that, send me an email and I will see you soon.